As you may recall, in gases there is a lot of empty space between the molecules. Therefore, when the gases mix together, the molecules can easily intermingle. As a consequence, gases are 100% miscible, or mixable with each other. When we mix various gases together, we find that the pressure of the mixture of the gases is simply the sum of the partial pressures of each of the individual gases, as we see here. So here we have three gases: helium at 1 atmosphere, nitrogen at 1 atmosphere, and oxygen at 1 atmosphere. When we mix all three of these gases together, we get a total pressure of 3 atmospheres, which is simply the sum of each of the individual gas pressures. This is known as Dalton's law, and Dalton's law can be expressed as the total pressure of a gas equals the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, and so on, until we've included the partial pressures of all the gases present in the mixture. We can also introduce a new concentration unit for gases, which is the mole fraction, represented by the symbol chi here. The mole fraction of gas A simply equals the number of moles of gas A divided by the total number of moles of gas present, or equivalently, the mole fraction equals number of moles of A divided by the total number of moles. Knowing the total pressure and the mole fraction, we can also use this to calculate the partial pressure of the gas, using this formula here, where the partial pressure of gas A equals the mole fraction of gas A times the total pressure. In a study of oxygen uptake by muscles at high altitude, a physiologist prepares an atmosphere consisting of 79 mole percent nitrogen, 17 mole percent of oxygen 16, which is an isotope of oxygen, and 4 mole percent of oxygen 18, another isotope. The isotope oxygen 18 will be used to determine the oxygen uptake. The total pressure of the mixture is 0.75 atmospheres, so this represents P total, and it's used to simulate high altitude. In this example, we are asked to calculate the mole fraction and the partial pressure of oxygen 18. The starting point here is the 4 mole percent of oxygen 18 that were given in the question. The definition of mole percent is simply the number of moles of a gas divided by the total number of moles times 100%. If we compare the definition of mole percent with that of mole fraction, we can see that they're actually very similar. Mole fraction is simply the number of moles of the gas divided by the total number of moles, so it's just not expressed as a percent. So we can convert from mole percent to mole fraction by dividing our mole percent by 100%. Doing this gives us a mole fraction of 0.040 for oxygen 18. Next, we can calculate the partial pressure of oxygen 18 using the expression the partial pressure of a gas equals the mole fraction of a gas times the total pressure. We were given the total pressure in the question, 0.75 atmospheres, and we've just calculated the mole fraction of oxygen 18, 0.040. So substituting these values into the question and plugging the values into our calculator gives us a partial pressure of 0.030 atmospheres, which is our final answer. In this example, 1.35 liters of a gas mixture at 25 degrees Celsius contains each of the following gases shown below: nitrogen 215 torr, oxygen 105 torr, and helium 117 torr. The first part of the question asks us to calculate the total pressure of the gas mixture. To do this, we just have to use Dalton's law, which tells us that the total pressure is just a sum of the partial pressures of the individual gases. In this case, we have nitrogen, oxygen, and helium. And substituting in the values of the partial pressures for each of the gases, and then adding up the partial pressures gives us a value of 437 torr as the total pressure. The next part of the question asks us to calculate the mass of nitrogen gas from the partial pressure of nitrogen. So the strategy here is to convert from pressure in torr to pressure in atmospheres, then to convert from pressure in atmospheres to the number of moles of gas using the ideal gas equation, and finally to convert from moles of gas to the mass of gas using the molar mass of the gas. So in order to convert from torrs to atmospheres, we should remember that the conversion factor is 1 atmosphere equals 760 torr. Then, since we're given the partial pressure of nitrogen in torr, 215 torr, we can then solve for x, which is the pressure of the gas in atmospheres. So you notice that the torrs cancel, leaving us with pressure in atmospheres and plugging the value into our calculator gives us 0.28289 atmospheres as the partial pressure of nitrogen. Now that we know the partial pressure of nitrogen, we can use the ideal gas equation, rearrange it for N, which is the number of moles of gas, which gives us N equals pressure times the volume divided by RT. Now we just substitute the values in to the ideal gas equation, and we have the pressure, which is 0.28289 atmospheres, which we just calculated, the volume of the gas, which was given as 1.35 liters, and the temperature of the gas, which was 25 degrees Celsius, which we've converted to Kelvin, which is 298.15 Kelvin. Finally, we should recognize that since our pressure is in atmospheres and liters, we should use the value of R for liter atmospheres, which is 0.08206 liter atmospheres per Kelvin per mole. Next, we'll take a look at the units, and we'll notice that the liters cancel, the atmospheres cancel, and the kelvins cancel, leaving us with units of 1 over moles to the negative 1, which is moles, which is the correct unit for number of moles of gas. Next, plugging these values into our calculator should give us 0.015609 moles of nitrogen. Lastly, we just have to convert from moles of nitrogen to mass of nitrogen, and to do that, we'll use the molar mass of nitrogen, which is 28.02 grams per mole. And since we know the number of moles, since we've just calculated it, we can solve for X, which is the mass of the gas. Notice that the moles cancel, leaving us with a mass in grams, as we expect. Solving for X gives us a mass of 0.43737 grams of nitrogen. You'll notice, though, that we should have 3 sig figs, since the moles of gas is 3 sig figs, and the molar mass has 4 sig figs. So our final answer is 0.437 grams of nitrogen.